I first wanted to, and I know we just like opened up these modules, and so I wasn't going to go through a full-blown lecture because there is a substantial amount of content in these. A lot of it is kind of, there is a large amount of content, but a lot of it is repeated. So a lot of like ANOVA, you guys probably know ANOVA t-test, you guys probably know that. So a lot of it is reminders of things, but a couple of things I wanted to go over if I can get there. For those who, read a lot of different cross discipline papers, a lot of times statistics will have different names depending on the discipline, right? So I wanted to go over some of like ANCOVA, analysis of covariance. These are, let me go over the actual results. Oh, so I also added a whole lot, a bunch more videos to each of these sections, in hopes that in addition to the content, you'll be able to see that. So I wasn't going to go over all of these because there's so many of them. Bear with me. I think it's the next one. Yeah, multi-factor ANOVA. So a lot of, let's say that a little bit. So these interactions that we're looking at here, group treatment and in a categorical. So these, if this was a continuous variable, you'll, oh, this is easier to see, I think, down here. It is loading in as a categorical variable in this methodology. Now, that's because when you look at the output, the parameter estimates, it then kind of dummy codes it for you and looks at parameter estimates for you. So you definitely have to load it in as a factor and not a covariate. But you can also do this exact same thing in a linear regression model, right? By dummy coding the variables and then looking at the interaction terms therein. Also, if this was a categorical outcome variable, you could also look at chi-square or cross tabulations as well. So in determining which statistical method to use, in addition to the type of variable, the independent variable, the type of outcome variable, within that, there are also alternative methods that you can use. You can use this kind of general linear model in SPSS, but you can also just go to linear to regression and linear regression if the outcome variable, and then dummy code that, right? And so then also looking at the other output. Sometimes these are also called in linear regression interaction terms. Have you guys heard that term before, interaction term? And so in SPSS, in these models that I'm showing you, you can just build the model out and say, do an interaction term here. But another way to do interaction terms is to hand compute it, not hand compute it, but compute it in SPSS yourself, especially if they're two continuous variables or a continuous variable and a binary variable. So a 0, 1 type of thing where you go and calculate and you multiply the two variables together. When you do that, you do have to center the variables before you multiply them. Does anybody know why you have to center them before you multiply them? So you can interpret it right, but it's mainly because of multicollinearity, right? So if you multiply them together and don't center them, it reads as almost identical. So to the other two, it's like the correlation is like a 0.8 or something like that. So you need to center them in order to avoid multicollinearity. And I've actually seen dissertations and theses where people forgot to do that, and it exaggerates, what it does is it exaggerates your standard error, so it biases the significant, the p-value significance. So if you think of significance is a calculation of the parameter and the standard error, those are the two things that go into the t-statistic. If you have a huge amount of multicollinearity, it messes with the standard error, so it misinterprets the p-value. So there were two of the big takeaways I wanted to talk about with the ANCOVA and the multifactorial, the two-way ANOVA bits, is that these can also be, let me simplify that. The main takeaway is you will find in the literature that a lot of those statistics are called multivariate regression, and they use interaction terms, right? Rather than what they're calling here ANCOVA, or what I'm calling here ANCOVA. So it's not a completely different statistical method. It's just called something slightly different, and they dummy code it rather than using it like this. So that's the one thing I really wanted to point out, so that when you're looking at research, you're not like, oh my gosh, what is this method? The second thing with the next thing I really wanted to point out is the repeated measures ANOVA. So repeated measures is you measure the same thing repeatedly across time, either pre-post test, or usually that's what it is, pre-post test with repeated measure ANOVA. Usually you do want some sort of treatment condition with repeated measure ANOVA. That's originally what it's designed to do, is include that randomization, because it doesn't account for covariates very well. You can do repeated measure ANCOVA, but it doesn't allow for like quite as many covariates. You can also do this in regression, the repeated measure aspect. But when you do repeated measure, because there's a dependence of the repeated measure, you actually need to bump it into a multi-level. So repeated measure ANOVA and repeated measure ANCOVA can be done in a regression model, but then it needs to be done in a multi-level model to account for the dependence of the data. So a longitudinal multi-level model, which is time points nested within individuals. Okay. Any questions about just those two additions to what you'll be going over?
Practical.
Please, practical question.
So in R, usually we do this, especially like the regression.
In R.
Yeah.
All right, well, we'll see if I can.
Is it long format? So like each participant has multiple rows, or each like one for each point maybe. And it looks like SBS one for like one for each column. I was just curious if it mattered if you were able to run it both ways in this case. It always wants, each measure each time.
Yeah, in SPSS, each measure, that's a good question. So we're talking about wide versus long formatting. So each in repeated measure ANOVA and ANCOVA, each time point needs to be its own column or its own variable. So each participant will have, or each row will have multiple depression time 1, depression time 2, depression time 3, and that's called wide because the data is wide, right? So the long format would look like each column would have multiple individual, multiple of the same ID number, and it would have an additional column of time. Does that make sense?
Yeah.
Do you guys want me to pull up an SPSS file that looks like that? Or do you guys understand what that is?
Yeah, I'd like to see it.
Okay.
Yeah, that'd be great to see it.
Okay. Bear with me as I sort through my data real quick. Let me think. We're gonna try for wide first. Maybe.
So usually are like be wide for data cleaning and stuff, and have it for every analysis.
Every analysis, okay,
Yeah,
that's cool. I mean, I guess, well, M plus, it just depends, and M plus it would just depend. Well, I think I know where I can find this. It is. Mm, 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 mm. Where are you, data? Here you are.
was it a data?
It should be wide.
Yeah, I was gonna say, if you want to do one.
Oh, that's a good idea. Okay, this one I think should be wide. Let me share. So we'll go to data view to be able to see it. So wide, so partner strain. So this is this is okay, we just ignore it, but we'll pretend this is straight. This is actually technically wide because they're dyads, so it's wide time and wide dyad, but you don't need to know that. We'll just look at strain. So this is caregiver strain is this measure. And so this is an ID number right here. And this is time 1, time 2, and time 3. Oh, time 4. Look at all those time points. So let me find paper that I did that is long. I think what the last one I did was long. Is this long? No, because it's a baseline study. I can download, like you said, the assignment for this week. Where'd you go? No, it's wide. Sorry, I'm looking for a long now.
Yeah.
All right, bear with me, you guys. Sorry. Stop sharing screen. I know where it is, but I worry it's going to be wildly confusing. But we got this. Okay. Good. There we go. Okay. I'm going to reshare screen here. And I think I'm going to make it a lot easier because I have a. All right. Thank you for your patience. Here we go. So here's an example of long where we have the case ID here. And here, this is a couple satisfaction index, 8181. So you look at the time variable here. And it's 1. And then if you scroll down long enough, I mean, there are like 1,000 people in this. You see time 2, right? So you see the same variable is conflict, couple satisfaction index, the CSI, and then it goes to 2. So the person, if you sort by case ascending, you see that this same ID 1000A is in here 3 times. But what we also see is they dropped out of the study. So we have missing data at time 2 and time 3, which is actually really common for this data set. Here's someone who finished, nope. They didn't finish all the waves. They just finished wave 1 and 2. And this data is super messy. So this is why cleaning data can sometimes, oh no, here it is. Okay. 1, 2, and 3. They have all of their time points, and just visually you can see their couple satisfaction increase from baseline. So the intervention for this person worked. So that's good news. And this person's relationship satisfaction was in the pits, and it got like marginally better. But this one's, bless it, it went well down. So this is also why looking at multi-level to see what maybe made that change trajectory on the couple level or individual level change. So this is a data that is long. And just to complicate things, this data is actually long because it's couple level data too. So you see the 1043 A and B, that's partner A and partner B. So this would actually go into a 3-level multi-level model. Time points nested within individuals, nested within couples. And then the same data I have wide. So you see time 1, and then for CSI, and then you have to scroll to see time 2 for CSI, and you scroll for time 3 should be, there it is, time 3 CSI is right there. So it is, you see just one couple ID because of the wideness of it. And the good news is in SPSS and data, you can restructure it. So you don't need to do any of this ever manually if you need to restructure it. And you don't have to do that for this class per se, but you can restructure the data yourself. And there are some great YouTube videos out there to do that, because it's the language of it. Restructure selected into cases, restructured selected cases into variables are your 2 options. It is not easily interpretable. It doesn't say in here wide to long, long to wide. So just because I'm just hyper obsessive about data cleaning, I always even still follow that YouTube video. I just have it up simultaneously when I'm doing it to walk me through it, because it's so easy to get mixed turned around with this. So that's just for your information. I can send you that whenever you're ready to if you ever have to restructure data. And as you can see in my data folder, I never really replace data files. So I always have a long version and a wide version if I'm using them in my folder, just so I don't have to repeat and do it. So I usually end up with, as I'm cleaning data, having multiple data files so that I can always revert back to the original raw or one version before the cleaning process. Did that answer? Pretty good.
Yeah, something else.
It just depends, yeah, on the model.
Okay.
It depends on how you're modeling it. So if you're modeling it in repeated measures, like what we're doing, then it does want them like that. If you when you go to mixture modeling, it will want it long.
Okay.
Because of the time points nested within people. So to capture the identification ID, it just depends on what it needs. But yeah, for now, it does want it like this in this model. Yeah, that definitely depends on the statistical test and having that knowledge and visualization. Like also when you if you move to M+, latent growth curve modeling, which you can test trajectories and curvilinear trajectories and cubic trajectories and all sorts of things. You can even in growth curve modeling, calculate or compute clustering of trajectories, so how different trajectories cluster as well. But that is all done in wide in M plus, because it wants you to identify each point, right? But the same longitudinal model can be done in multi-level model in M plus, but it needs to be long. So I can calculate the exact same statistic, whether it's latent growth curve modeling, but that's wide, versus multi-level modeling, but that's long. So it just depends on what question am I specifically trying to get at. Do I really just want the means of things, or do I want to try and more clearly manipulate that line and see what those lines kind of look like? And that also depends on how many time points you have. So if I have 2 or 3 time points, I'm going to probably do a multi-level model. If I have 10 time points and I want to see how that model increases and decreases over like specific time points, then I'm going to do it wide and look at latent growth curve modeling and see if I can have different lines. Because in latent growth curve modeling, you can estimate increased trajectory from time 1 to time 4. Time 4, I think it's just going to be flat, and so you can also estimate different types of lines in addition to curvilinear line. So it depends on your research question and the number of time points you have, and also sample size, of course.
Okay.
Cool. All right. What other questions about the modules in the class before we pop over to the multi-level analysis? Also, feel free to like email me or whatever with questions throughout the next 2 weeks I think we have. I don't anticipate you having all your questions right now. Okay. So I took the list, I don't even know if I did everything. How did you find the reading?
First chapter was
It was a lot of equations. I do think it was probably too much reading, and I apologize for that. I think next week we'll just do one chapter at a time, and we're not going to get through this whole book, but I think that we agreed on chapter 9 for next week, and then the next time, the week after that, chapter 12, sample size and power analysis, and then we'll see where we are. But this was kind of like a throw into the deep end. I'm curious from your perspective. Let's start with chapter 1. What were some big takeaways for you for chapter 1, or questions that you have?
I'll say on my end, I only found it last night. I didn't realize it was posted. So I'll follow along with y'all, but I don't have something to add to the conversation.
So I think one really kind of important thing to go over as you're just consuming information is page 3 and 4, which are like the fallacies or the issues with running things not as multi-level models. And for me, it was nice to revisit these, like the ecological fallacy, because I do run a lot of statistics looking at like community rate of primary care providers in the community, or proportion of community primary care providers, or percent diabetes in a given community, and how that affects individual outcomes, right? And reading this, I was like, oh, I definitely need to be running these multi-level. I just have been doing them in regression. So being like constantly reminded that like there are good reasons to run multi-level model, even though it's complicated, because it biases your results, even if you're not making the clusters, right? Like it's counties, which is not necessarily a natural cluster. But if I'm looking at cluster level variables, then I probably should be running these multi-level model. So that was a big takeaway for me, like, oh yeah, I need to be doing that. What about?
The aggregate and disaggregate made sense, that's something we need to.
Yeah. Which is kind of what I'm talking about, right? Like I'm almost disaggregating the county level data by putting it on the individuals, like there might be 10 people in that county, but like I'm saying, they all have, the same rate of percent diabetes in the community, right? So I'm disaggregating that data versus aggregating, which it can be important if that's part of your research question, right? It just wasn't necessarily like I'm talking about the aggregation, like student grade average, right? Like maybe that's or pass pass rate or whatever, like in a school, like that could be important to a certain extent, but at the same time, when I'm thinking about this, I like to remember the silly saying that my first stats teacher said is that means lie. Like they kind of sometimes, because it's such a variety and you're clumping them down into numbers, sometimes they hide that the truth of the variability from the sample. So remembering that I think is also important in how you're modeling, but sometimes you don't have a sample size. So when we'll get to sample size, obviously, to run these models, you kind of just have to do the best that you can and like mention it in the limitations, right? Like these fallacies could be really important if you're running this as a one level regression model. Acknowledging this in your limitation and direction of future research could be really important as well.
Yeah, when you put it as a correction procedure, that was 100% of what they were talking about there.
Yeah, and he wasn't it was a little bit of hand waving, like, oh, there's this correction procedure that you can do, but I don't think he gave like the actual calculations for it. And I
described it at least. My understanding was it's if you're running by a one level total regression, but it really should be multi-level, you can use this correction procedure to estimate.
Right, he described it right, but I don't think he gave the actual calculation, did he? Maybe he did.
It's on page 5.
Oh yeah, he gave the equation, correction described by the effect one. I even underlined it, I just didn't remember it. But I think this is done by hand because I have never seen this in M+ or SPSS.
I've never seen anybody use it. It's just trying to.
And yet it was originally computed in 1965 and just never came into practice. But I think it does seem important, especially if we're thinking about it makes me also think about interclass correlation, which is one way to figure out if maybe it really does need to be done in multi-level models. So maybe you do have some clustering and you do interclass correlation, and it says like not a whole lot of the variance is accounted for by this top level. Well, I think that's some indication that you probably are safe to not do it as a multi-level model if your interclass correlation is low, and I don't know those exact cutoffs, but I think that could be a good place to start. Especially if you get pushback from reviewers or you're trying to think of like how really to run this given your sample size, looking at interclass correlation. Okay, am I worrying and fretting about this for a reason or not a reason? I think is good to, and it could be part of that data cleaning, data investigation, understanding your univariate normality distributions, your multicollinearity, and also if you know there is some clustering in your data, a little bit of dependence naturally in your data, looking at the interclass correlation could be another aspect that you run in data as well, part of your data cleaning. And if you do have it and can't run it, then I think the correction could be really appropriate.
Because the other downside of the model, assuming that it's a requirement of sample size.
Yes, particularly on the top level, right? Like, let's say you have some dependency, but you only have like 2 clusters. Well, you can't have 2 on the top level. That's like saying I'm gonna I'm gonna run a t-test with 2 people. You can't do that,
Mhm.
right? So you think of that top level as also being a sample size that needs to be sufficient to estimate an effect.
Mhm.
And then if you're doing any sort of interaction on top of that, that is more power, statistical power that you need on top of that. But yes, you're right, it does need power. So what were your big takeaways from chapter 2?
I was just gonna say, they were really.
Oh, no, it's fine. So I think, one thing that people get really cross-eyed sometimes easily is the equations. And I think that he does a good job explaining that, like, the baseline equation, the first level, with the B's in it, the betas in it. And then, and that's the level 1, right? And then part of multi-level model is then you're going to estimate each beta. So then each beta has a parameter, right? Let me show you so like here, this one right here is the baseline equation, right? So this is like just a basic linear equation that this is our outcome variable y, or a dependent variable, and then b0 is our intercept, and this is b the slope or the estimate for variable 1, and this is just a regular multivariate regression line, right? And then you always have error in your estimation as well. So this is kind of the y equals mx plus b type of linear line, but with multivariate, right? Okay, so that with the J's and the I's kind of explode your brain a little bit. The I's are just individuals and the J's are just clusters, okay? So it's like the beta parameter given for each individual, the accumulation of each individual within each cluster. Okay, so that's the baseline regression line. And then with multi-level model, because we remember last week we talked about how you have that line, but we know that there's variability in that average line. Right? Okay, so then we talked about how the intercept and that line then becomes an outcome variable, right? When we're thinking about multi-level model, we're estimating it and then we're like, okay, well, I want to predict the variation in that line. So that's what those other follow-up equations are the equations for that line on the second level. Okay, so the outcome variable then, the outcome variable, the DV then is that beta, right? That we saw in those previous equations. And this is all on page 13 of the book. So then when it gets really, really annoying and complicated is we go back to you remember algebra and calculus way back in undergrad and even high school where it's a equation where it's y equals, and you have two letters, you have y equals x and z, and then you have to solve for z, and then whatever that equation is, you solve, you plug in and then you have a really long equation, but then you can figure it out because you only have one variable. Okay. That's what this next one is. Then you're plugging in these b's through this. Well, now I'm getting mixed up to this baseline equation, which gives you this bottom equation. Okay, so it looks really, really complicated, but really it's just kind of understanding the multi-level aspect and what the basic linear equation is, and understanding the multi-level variable, multi-level modeling of those slope estimates and intercept estimates. And so when you read about this, you'll understand what those equations are. And that's important in this one. It's not necessarily to test you over your memory of algebra, but just so you can like trace back and understand what the equations are. It's really rare these days for journals to require these equations anymore. I've seen some grants require these types of equations, like NIH grants, so it's important to know it so you can at least calculate it out. It's not as required anymore. But it's important to have a reference for, so in case a reviewer or whoever's on your dissertation is like, hey, I want you to put a equation and you know how. What else about chapter 2?
When they're trying to think like this stuff.
Yes. Yeah, oh, yeah. The different languaging all around it is wildly, confusing. How, it's like this developed in so many different disciplines and they all came up with different terms for things. And so trying to understand what each of that means can be challenging. So always going back to like, and that's another reason why going back to whatever their equation is important, because then you can understand, okay, I don't know exactly the term they're using, but I understand, like, because the equation is always the same.
Yeah.
I understand what they're doing because I understand this equation. Okay, so they're calling this, right? So it is kind of the basic math that sometimes makes interpreting the words easier.
Yeah.
Okay. So let me know if a question pops up. I'm gonna go through an analysis using M+. How does that work? All right, I'm gonna walk you through the input and then the output. This is a 3-level longitudinal model. You should also know that it is because it is couple level, because it is a pre-post test. Oh, this might be a pre-post test. That means that we cannot see random effects for slope and intercept. So this model is a little bit confusing because if you think of the degrees of freedom, if you, I'm gonna draw this in the board. I'll move this over here. It's supposed to be getting you. You guys can see anything. Because I'm also sharing screen. Okay. So. Try to draw it. We have our regression line that we're trying to estimate. An intercept and a slope, right? Are the two things we're trying to estimate. B naught, B0 is our intercept. Can you guys see this? Can you see this? Yeah, are you sure? Okay.
Yeah, I can see it.
Yeah, there's the little subscripts are hard to see, but
I'll move you a bit closer. Okay. So B naught, which is the intercept, right, zero, and B one, we're just pretending that we all have one. Okay. So we're estimating two parameters, right? So if we're estimating two things, we need a degree of freedom. We need 3 degrees of freedom. Right, because the intercept takes up 1 degree of freedom, we're estimating 1 thing, and 2, so 3 minus 2, you need at least 1 degree of freedom to be able to do a parameter, right? It's like basic stats 101. So when we're doing, because I only have 2 time points, on 1, on 2, I have to freeze one of these things in order to estimate the change. Okay, it's not ideal, but like that's what we have to do with this type of data, so we can estimate, but we can't necessarily estimate. We can estimate the average intercept, but we can't estimate variability in the intercept. Okay, so we have to fix this one, and the random intercept is only this. This, it's not like real practice, you know, like you want 3 time points, like there will be reviews or like, we can do this, and like, well, you can't technically, I'm not estimating it, but. So sometimes you have to argue a little bit to review about this. But that's what we're about to see is I'm just, because I only have 2 degrees of freedom, because I only have 2 time points, I can only estimate, or I could estimate the intercept, right? But because there's an intervention, I'm more interested in change. So I choose the only estimates here. And because also it's coupled, there's only 2 couples, when we go to the third model, it's the same issue. Questions about this and what we're about to go over? So it's so I just am trying to set you up to realize that it's not a full breadth of what it has to do, because and I will try to find better multi-level data in the future. All right. Yeah, I don't think I have any of it right now. I can find it. Okay. So how much of this M plus output do you want me, input? Ooh, oh no. Oh, actually, that's not a terrible place. Where is it? Huh. Do you want me to go over the input in great detail or just kind of the multi-level aspect of input?
I think everyone output and then.
Okay. So. So in M plus, you have within and between, so it kind of goes back to using like ANOVA and repeated measure ANOVA estimates of within and between effects, which is lovely and confusing. So between is the first, within is the first level model. So you see I have a CSI on time, so that's time. So CSI, the way M plus works is you're thinking about your outcome variable is regressed onto your input variable, which is technically what the term means, regression. So regressed onto CSI on time 1. And I have some interaction terms here. And looking at the interaction between time and marital status, which is married or cohabiting. So then I'm looking, because in M plus, when you move the outcome variable to the next level, that's your random effect. It's very, very simple and it's easy to make mistakes. If I wanted, you move it to the next level and the next level. And this is the between effect. Okay, so the outcome. So I'm gonna take it all back. I actually modeled this. I forgot. I modeled this I bootlegged it a different way. I bootlegged this model by no, ignore this if this confuses you. So I looked at regression on the regression of CSI on time. So assuming that regression model and centering it, regression on time. And if you move that intercept, the intercept of this line up, that is actually the average of the slope up here. So I'm looking at the average of the slope but through the intercept. So I fixed the slope, not the intercept, and this one I forgot, because you move the intercept. If you move the intercept of time, it's in the mean up, the intercept of that output is so if I were to if I move on to be center, and I capture this, because it's a subtraction of these two things, it is actually the difference, because I'm not necessarily going to slow down the difference between the two. I can then model upon that. And I think that's kind of what they call the change. This is the change. I forgot I gotta say that way, but so that's, we're modeling this here, right? So how minority status affects that difference effect, basically. And marital status, number, parenting status, which is child, and property status. Yeah. We actually aggregated this. Poverty status was household income, based on household income and total number of people living off that income. So we only had individual reports of income, and so we did aggregate that to calculate poverty rate, because poverty is a household level variable, not an individual level variable. So we aggregated it to create a new household level variable, I guess. And then marital status, because all of this is self-report data. Or individual report data, sorry. We had some couples where one person was like, yes, we're married, and the other member of the partner was like, we're cohabitating. And we're like, okay. So as a group, we made a decision that when that would happen, we would choose one or the other. I did this like 7 months ago, I don't know what we chose, but like as a collective group, we decided that one person is like, I think we decided if one person says we're cohabiting, like the likelihood that they're not married is higher than like they are married, because it's hard to forget if you're married, but some people who live together for a while are like, married, right? So that's how we argue it. So this is also aggregated data, and so is child. We just did the highest number that one partner reported. Because if one person is like, yeah, we're married. Well, I don't know. I think like I could see like stepchildren or parent, you know, maybe they co-parent with someone outside the home, and so it's not like the kid's not there full time. And to be fair, there was also a parenting measure, and so we had some people complete the parenting measure, and then they would write on it for our dog. And I was like, oh, it's not. So I also wonder now that retrospectively looking back, if like some people were saying that their child is a dog, a furry pet, which fair enough. Okay, so the output here. Go all the way down. This is just talking about, this is your interclass correlation, which is fairly high. And then on the couple level, there's a lower interclass correlation, which retrospectively, I probably should have reported that at the outcome in this study, but I did not. Average cluster size for the couple level ID, 3. So they're not like, there weren't like a ton of thruples. It was that because we had 2 time points, right? Time points nested in the, really there should have been 4, right? But because of the missing data, we had an average of 3. Does that make sense? So each couple had 4 different data points that went into it. This is just the how M+ does covariances and correlations. It's not quite as pretty. Your means, estimated sample statistics. This is for the between couple effect as well. They estimated that each the given variable at the appropriate level that you tell it to. And this is where we would get our model fit information. Because this is M+, it assumes at baseline, everything you're doing, you're trying to run a structural equation model. So, but because I have no degrees of freedom left, and I don't have any latent constructs, you see the RIMZ and the CFI and TLI fit absolutely perfect, but I don't have any latent constructs. I'm like, so of course it would. If it didn't, we would be very, very concerned. So here we see time on CSI. It improves 3.55%, 3.55 points. So this is how we read M+ output, but with the within level first, then the between level. And then the other between level. And it sees your estimate, your standard error, your estimate divided by the standard error, which is your T statistic to calculate your p-value. So that's why I was talking about bias earlier, because this is genuinely just straight up how we calculate the T statistic. And then we look at, one of those tables to see if it's statistically significant or not, is the estimate divided by the standard error, not the standard deviation, but the standard error. And then, so you're going to look at your p-value and your estimate here. And this is your raw unstandardized estimate. And you can interpret that. What this is, the new, in M+, you can also tell it to create new parameters. Like if you want to calculate effect size using Cohen's D coefficient, you can tell it to do that. And you can also tell it, like if you have simple slopes, if you have interaction term and simple slopes analysis, you can tell it to calculate the simple slopes as well, and it'll output all of that for you. So then the standardized model. So in SPSS, you see the unstandardized. In the same table, you see the unstandardized, standardized, standard error, standardized, and then the a confidence interval, and then a p-value in there somewhere, right? Sometimes if you're lucky, it'll also shoot out a effect size in that one table, but M+ doesn't do it that way. It's all this unstandardized together, all the standardized together. And then if you request it, which I don't remember if I do in this model, yep, here it is. You get the confidence interval of the models. So you have the same CSI, and then you have to, in your mind, know, do I want the 90th percentile? Do I want the 95th percentile? Or do I want the 99th percentile, right? So if I want the 90th percentile, I have to remember my beautiful little normal curve and that 5% on each side, right? And this is the estimate in the middle, if you remember, up to the unstandardized. And so then I would look at the lower bound of the 90th%, which is 5%, and the upper bound. If I want the 95th percentile, which is what I typically report and what you see in SPSS, you have to remember 95, that leaves 5% and 2.5% on either side of the normal distribution. So you have to go back and remember all of those lovely normal curve estimations and all of those things and what the 95% confidence interval really means, which is nice because M plus will definitely always keep you honest and remember your roots, which I assume R does too. R always makes me remember like my roots of like basic statistic calculations whenever I go to it. And this is the standardized output, and that's all of the output here for M plus. Questions?
You have to, for your international term, that your action term with M plus to the human model.
Yeah, I should run it. M plus,
It's the bottom there.
yeah, and actually, like I said, I did this 7 years ago, and there's a better way to do it now. Let me see if I can find a way that I've done it recently. I think it was in this.
This is what we're doing, I mean, set of each variable and then let the model do interaction. Interaction forward.
Yes, yes. Let's see if if I did it here. Yes, okay, let me see, hold on. Maybe I did, ID random within. There's a new way I really prefer doing it now that I'm trying to find, so just stick with me just a second here. But I do have this paper. Yes, simple stuff, here we go, okay. Input, output. So. In M plus. In this define area. So M plus binary outcomes, it is. Standard for it to center binary. So I don't like 0 and 1, I don't have to do anything with that, it does it all. For continuous, it does not. So what I like to do is, or what M plus is now recommending you do, and I've started to do it and it makes it really easy. Is I standardize. So that way when I go to simple slopes, I can do a standard deviation below the mean is 0 and a standard deviation above, which makes it a lot easier to calculate the simple slopes. If I'm just looking at this, rather than like trying to find what the mean is, I could just say 0, -1, and +1 are standard deviation below and above the mean. So here is where I standardize. This is just the family outcome. And I create an interaction term between rurality and the standardized variable. So in M plus, you have to say which variables you're going to use. And if you're going to create a new variable, it has to be the last in the sequence. And what I'm calculating is a Poisson regression. So I said count is condition, so number of health conditions. And it was a small sample size, so it wouldn't run a regular maximum likelihood. So I had to run it in a Bayesian estimator using Monte Carlo integration method. So when you run it, it just like so anyway, if you'll see here, I feel a cough coming on. This is conditions, so my outcome variable regressed onto all of the variables in this model. And actually, this isn't even a multi-level model, it's just an interaction term model, so, because it's, I guess this is my baseline model. So I was curious how people present. But this is what I was talking about, like maybe, like with these rurality, variables, maybe I should be looking more at like county, at like rurality as a county level or a census tract level information, but, this paper is already published, so, you know, next time. Actually, is it? No, it's not published yet. It's at, I just gotta revise and resubmit. It's at Family Systems and Health. Hopefully they'll get back to me soon. Anyway, I digress. So I have I named this parameter. So the conditions regressed onto McMaster's. I'm saying, I just want to tell you in plus that I'm going to name this parameter B1. And then this interaction term between rurality and McMaster's, I just want to name it B2. So then that helps for when I come down to here, because I know that there's an interaction, and I'm just curious about the simple slopes effect. I create model constraints, I create some new variables. So I want to know, and this is just going back to basics, y equals mx plus b, right? So I want to know what the effect of family is when I look at just rurality. So rurality being 0, right? So that's B2, my interaction term. So this is just a basic, so that's rurality. And then the next one is when rurality is scored as 1, which I think is someone living in a rural area, and 0 is not. So I can, within M plus, just calculate what my simple slopes are with those interactions, which is nice. It would make what I said earlier about standardized, if I wanted to look at, in this model, rurality is my moderator, right? So the main effect B1 of family on my outcome, versus, and I know that says rural 1, but that's just because it's what the moderator is, but it's conditions, right? Dependent on rural status. But if I wanted it the other way around, I could still do 0, -1, and 1, and because I standardized it up there. So then I go to my outcome variables, my output, and it looks the same. Again, this is just a regular multivariate regression. And so I see that the interaction term is statistically significant. Oh, thank goodness, I already did this simple slopes analysis. And then we also see that family is a significant predictor of conditions. So in a negative direction though. So the better the family quality, the fewer health conditions they have. Keeping in mind this is Poisson, so we will be interpreting the odds ratio, not, so I have to hand calculate it in M plus. But anyway, the new additional parameters, we see that only people with not in rural areas observe this effect, but people in rural areas, family does not impact statistically significant, right? So keeping in mind way up here what these columns mean. That rurality, that the people in rural areas, family is not a significant predictor of conditions, only people in urban or suburban areas. So that's what that means. And the reason why you look at it at the simple slopes is because of the interaction. Those are a really long way of answering your question, right?
Yeah.
Any other questions? Curiosities, comments? Okay, well, this book, and I realize he's had like another edition since. This is the second edition. We have a third edition. I'm curious to look at it. I think I might buy it, but we'll just keep with the second edition because it's free. So I think next time if it's okay with you guys, we'll plan to read, just one chapter. We're just gonna read chapter 9. Does that work? Okay. For this, and we'll go over. So factor analysis is the next model? Surely not. Oh, Mancopa? The next lecture is on, or is it on mixture model? No, mixed linear. model.
Vancouver.
Yeah, it's what, oh yeah, it's Manova and Mancoba, okay, so. That's what we'll be lecturing over, lecturing, yeah, asking questions, intentional questions over. Manova and Cova, and talking about chapter 9, cross-classified multi-level models. Does that work for everybody?
We don't have that data. Right. It's all-
Yeah. Just thought there were too many of them. We probably, it's not, yeah, it's mixed linear. Yeah, we don't, there's not a whole lot of time spent on Manova and Mancoba, is there? Just kind of up to mixed linear models. Which is multi-level models, right? All right. Questions, comments, concerns? I mean, we used the whole time almost this time. Do we still want to keep it at an hour and a half, or do we want to pop it to an hour? Thoughts?
Keep it long, and if it happens to be short, that's
All
fine.
right. All right, very cool. All right, well, hopefully this was moderately helpful for you guys. Again, I'm just trying to structure these around what works for you guys, so let me know either now, through an email, whatever, if you want a different type of format. It is more discussion based. So, discuss whatever you guys bring, and, you know, I might highlight a couple of things here or there that I think are particularly important, but this is kind of my idea of how this format works, so. Okay, good, okay. Well, out there watching the video and video land, if you want to prefer a different format, just let me know. You popped off. Do you have
Yeah.
a question?
No, I was just saying thanks. I think the next one, I just went to my follow-up appointment. I'll have to be virtual one more time, but
Yeah, stay safe out there. Yeah.
Okay.
Any other questions?
Thank you. I enjoyed getting to see it today.
Oh, God, I'm glad it was helpful. One day I might have the fancier device where I don't have to turn my laptop around, but yeah, time will tell.
No, it's good.
Okay. Take care,
Thank
you guys. Lovely to see you all.
All right, thank you.
Bye.